This presentation is part of the TI in Focus AP Calculus video series. In this video, I'll discuss a specific concept associated with the 2017 AP Calculus exam, free response question BC5, namely, improper integrals, type 1 infinite intervals. My name is Steve Kokoska. I'm a professor at Bloomsburg University in Pennsylvania, and I am a former AP Calculus chief reader. Here's an outline of the information presented in this video. I'll begin with a little bit of background information, and then I'll consider a geometric interpretation of a type 1 improper integral. And this will lead us to a precise definition involving limits. I'll consider a few examples and use some technology. And finally, I'll consider the concept of convergence or divergence by comparison. Recall that in the definition of the definite integral of f of x from a to b, we assumed that the function f was defined on a finite interval, and that f did not have an infinite discontinuity in this interval. Now, we want to extend the concept of a definite integral to the case in which the interval is infinite. And similarly, we can extend the concept of a definite integral to the case in which f has an infinite discontinuity. In either case, the integral is called an improper integral. I really want to understand where the definition for a type 1 improper integral comes from. So let's consider the infinite region R that lies under the graph of y equal 1 divided by x squared, above the x-axis and to the right of the line x equal 1. Now it seems reasonable that since the region R is infinite in extent, then its area should be infinite, but not so fast. Consider the area of the part of the region R that lies to the left of the line x equal t. Well, this is a finite interval 1 to t, and we can write an integral expression for this area and evaluate to find the area in terms of t. And here's a figure to illustrate this result. Notice that the expression for the area of a part of the region R is less than 1, no matter how large a value of t is selected. So let's consider the limit as t increases without bound. Well, the limit here is 1, and this limit suggests that the area of the shaded region, part of the region R, approaches 1 as t goes to infinity. It also suggests that the area of the infinite region R is 1. And here's how we express this result mathematically. This illustration and limit process leads to the following definition of an improper integral of type 1. If the integral from a to t of f of x dx exists for every number t greater than or equal to a, then the integral from a to infinity of f of x dx is equal to the limit as t goes to infinity of a to t of f of x dx, provided this limit exists as a finite number. Now, we can also consider an infinite interval in the other direction. So, if the integral from t to b of f of x dx exists for every number t less than or equal to b, then the integral from minus infinity to b of f of x dx is equal to a limit, again, as t goes to minus infinity, of the integral from t to b of f of x dx, and again, provided this limit exists as a finite number. These two improper integrals are called convergent if the corresponding limits exist, and divergent if the limit does not exist. There's one more case to consider, if the interval is infinite in both directions. If both of these improper integrals are convergent, then we define the integral from minus infinity to plus infinity of f of x dx as the sum of the two associated improper integrals. And note that any number a can be used here. Here's a closer look at this definition. First, remember that infinity is not a number, it's a symbol. And you can't do arithmetic with infinity. So you cannot simply find an antiderivative of f and then evaluate it at infinity or minus infinity. Evaluating a type 1 improper integral is really a two-step process. First, evaluate the definite integral and simplify if possible, and then evaluate the limit. And any of the improper integrals in this definition can be interpreted as area, as long as f is a positive function. So here's how we formally define the area of a region of infinite extent. Let's try an example. Determine whether this interval is convergent or divergent. Well, first, I need to recognize that this is indeed a type 1 improper integral. The interval is infinite, and as an aside, there are no infinite discontinuities in this interval. So use the definition of a type 1 improper integral. Find an antiderivative, evaluate or use the fundamental theorem of calculus, and then find the limit. And so the integral is convergent. And since the integrand is positive, even though it sounds contradictory, the area of the infinite region is 1 minus 1 over e. Here's a technology solution to this problem. The TI-Nspire can evaluate this improper integral. And notice that we don't need to type in the strict definition of the improper integral involving a limit. And here's a visualization of this result. The shaded area is part of the region R, which has area 1 minus 1 divided by e. Let's try another example. Determine whether this integral is convergent or divergent. Well, again, this is a type 1 improper integral. The interval is infinite. Use the definition of a type 1 improper integral, find an antiderivative, and use the FTC, or simply evaluate. Here, the limit is infinity. Now remember, this is a symbol which indicates the behavior of this limit. The limit doesn't exist. It increases without bound. And so the integral here is divergent. Here's a technology solution to this example. The TI-Nspire indicates the improper integral is divergent by returning infinity. And here's a visualization of this result. Let's try one more example. Let's determine whether this integral is convergent or divergent. Notice that this is an infinite interval, this time from minus infinity to plus infinity. So we need to split this up into two separate improper integrals. Remember, we can split the interval at any value, but 0 is often a good choice because the evaluations are usually easier. So I'll write the original integral like this. We can work on either improper integral first, so I'll try the one from 0 to infinity. Use the definition of a type 1 improper integral, find an antiderivative, evaluate, and find the limit. Since the limit is finite, this first improper integral converges. Now note that if it were divergent, we could stop right here. There would be no need to consider the second improper integral. The original would diverge. For the second improper integral, use the definition of a type 1 improper integral again, find an antiderivative, evaluate, and find the limit. Since this limit is finite, the improper integral converges. Now, finally, since both improper integrals converge, the original improper integral converges. And we can write this mathematically as the original improper integral is equal to pi. Here is a technology solution to this example. The TI-Nspire is able to evaluate this improper integral. All the anti-differentiation and limit evaluations are going on in the background. We don't need any additional command here. And here is a visualization of this result. The total area under this curve is exactly pi. That's pretty amazing. Sometimes it's impossible to find the exact value of an improper integral. For example, we might not be able to find a closed-form antiderivative. But it still might be important to know whether the improper integral is convergent or divergent. So it seems reasonable to compare known old integrals to a given new integral in order to draw a conclusion. To carry out this process, we can use the comparison theorem. Suppose that f and g are continuous functions, such that f of x is greater than g of x is greater than or equal to 0, for x greater than or equal to a. If the integral of f is convergent, then the integral of g is convergent. I kind of think of this as saying if the larger function or the integral of the larger function is convergent, then the integral of the smaller function is also convergent. If the integral of g is divergent, then the integral of f is divergent. So similarly, if the integral of the smaller function is divergent, then it seems very reasonable that the integral of the larger function is also divergent. Here's a graphical illustration of the comparison theorem. If the area under the graph of f is finite, then the area under the graph of g is also finite. And if the area under the graph of g is infinite, then the area under the graph of f is also infinite. Now, the reverse of this theorem is not necessarily true. If the integral of g is convergent, then the integral of f may or may not be convergent. And if the integral of f is divergent, then the integral of g may or may not be divergent. Here are a few more improper integral problems. In Part A, determine whether each integral is convergent or divergent. In Part B, find a value of c so that this integral converges, and evaluate the integral for this value of c. I hope this video provides some insight into Type 1 improper integrals, a few AP Calculus type problems, and the use of technology to solve these types of problems. And just a reminder, there are lots of valuable resources on the TI website. There is material there involving technology and calculus, classroom activities, and lots of calculator tips and tricks for test success.